Good morning all. So today's class we're going to study is called the single phase AC system with series RLC circuit. Let us consider RLC series circuit here. So this is look like the RLC series circuit, which is the different RLC series circuit which are connected in series here. So this is my R, this is L, and this is C. So here you can say this is the voltage which is we are applying here, and this is the current I is going through B through your element, you can say. So whenever this current flows through this RLC's element, so this is going to give the drops here. This is VR drop, and this is nothing but your VL drop, and this is the VC is nothing but the drop across the capacitor. If you want to draw a vectorial diagram for this electrical network, so what I try to do is I will take the current as a reference. I will take my current as a reference here. I will take the current as a reference, and I will take the each element alone, and I will try to draw the vectorial diagram. So suppose my pure resistive element, if it is there, then what is my VR and I behavior? My VR and I behaves is in phase, isn't it? So both are in phase if it is a pure resistive. So I can write here, so these two are in phase. This is VR and I are in phase. IR is nothing but I into R drop. So this is the VR vector I am getting. Similarly, if you write the relation between your VL and I, that drop across the inductor, and the current relation, if it is a pure inductor, then your current lags voltage by 90 degrees. So that is the concept you have already gone. So with that I can write this is my VL, this is my VL, or you can say this is IXL. Here my current lags this VL voltage by a 90 degrees. So this is the meaning. Now if I want to draw the phasor diagram for this capacitor alone with respect to this current, then for pure capacitive circuit my current leads voltage by 90 degrees. So my current leads voltage by 90 degrees. So this is VC, nothing but I into XC. Now you see my current leads this voltage by a 90 degrees. So this is what the meaning. And now if I want to calculate what is this supply voltage, is nothing but the vectorial summation of VR, VL and VC. So here if you see, this is the one VL vector, and this is your VR vector, and this is nothing but our VC vector. If you add these three vectors, so that the resultant vector is going to answer our supply voltage vector. But if you observe here in this diagram, your VL vector and VC vector are opposite to each other, or you can say 180 degree out of phase each other. So here you can take one note. Here. So here my VL vector and VC vector are opposite to each other, so therefore the summation, the adding of the both, or summation of both can be have a different possibilities. I can say suppose my VL, suppose my VL, if it is greater than VC, then my summation could be VL minus VC. It means some positive term will going to come. If my VL is less than the VC, then this is going to come VC minus VL. So this is what the negative terms will going to come. If my VL is equal to VC, then this is going to become a 0. Adding of the two values will be become 0. So this is going to get some positive value, this is going to get the negative value, this is become 0. So these are the three different cases can be occurs in this this vectorial diagram. So for understanding purpose or for to analyze this RLC series circuit, what I assume is I will assume that my VL is greater than Vs. I will assume this case. I will assume this case. And where my VL is greater than Vc. If my VL is greater than Vc, then adding of VL and Vc obviously comes over here. Adding up VL and Vc will going to come somewhere here. So the resultant of your VL and Vc, that is nothing but your VL minus Vc vector. Adding of your VL and Vc, where VL is greater than Vc, then this is the net amount of vector is coming. Now after getting this one, if you add this vector with respect to your VR vector, then you are going to get the supply voltage vector. The supply voltage vector you are going to get, that is nothing but I into Z, where my supply voltage and my current has an angle, that is the pi. So in this case I can say my current lags voltage by some pi angle, because in this condition my total circuit is my total circuit is inductive dominance. That's why my VL is greater is coming. So inductive dominance, then my obviously my current lags voltage by some pi angle. So that is what you are try to get. Similarly, if you talk the same kind of thing, and if you take this case, suppose if you take this case here, if you take if you going to take the second case, then the VL is less than VC. It means VC is greater than VL. So obviously my vector comes over here. So this is nothing but my VC minus VL net resultant vector, this one. And if you add these two, then this time my supply voltage will come here. This is the pi vector, and here my supply is equal to I into Z. So this is the second case. If you consider, then this could be the possibility of vector diagram is coming. Now in this case, if you see how will be the relation between your supply voltage and current, here is where here in this case my current leads voltage by some angle pi. It means my current is leading, means at this moment the condition my total network is capacitive dominance. So my total network is capacitive dominance, that's why I am getting VC is greater. VC is greater we are getting. So VC is greater than VL. So this is net amount of is coming in this down direction. So my voltage obviously lags current by some angle pi. So these are the two scenarios I am able to explaining here. Now we are going to take the first case and we will analyze the circuit here. So what is the case first? where my VL is greater than VC, then what is the different expressions we are getting. So that is what I want to talk here. If it VL is greater than Vs, then if you want to what is V is nothing but, it is nothing but you can take VR square plus VL minus VC square, or you can write it is IR square, and this is IXL minus IXC square. So if you do this one, then you are going to get something like this, R square plus XL minus XC square, or you can say this is I into Z V, where Z is nothing but this one. Okay, so this is called the impedance of the RLC circuit. This is called the impedance of the RLC circuit. And if you want to draw the impedance diagram, then this is what the impedance diagram will come. R, this is XL minus XC, and this is my Z, where this is the angle pi, you can say. So from this impedance diagram, again you can write what is this cos pi is nothing but R by Z, or R by what is Z here, you can write R square plus this is XC, XL minus XC whole square, you can write. Or if you want to calculate what is tan pi, then this is the tan inverse of XL minus XC by R. So these are the different relations I'm getting from this impedance triangle to analyze the what could be the possibility of formulas we can able to get. Suppose if my XL minus XC is increases, then what is my pi? Pi also increases. So that is the point I can highlight here. And if I XL minus XC decreases, then my pi is decreases. So how this XL minus XC decreases, and this is what you can talk here. If my XL is equal to XC, if my XL is equal to XC, then what could be my pi angle here? What could be my pi angle here? My pi is equal to 0. My pi is equal to 0 degrees. So this is what, whenever the XL is equal to XC. Pi is equal to 0 means what? It is a purely resistive circuit. Pure resistive circuit. Resistive load, isn't it? Cos pi, where pi is equal to 0 means your voltage and current are in phase. That in current voltage and current are in phase when the condition is the load, if it is a resistive, pure resistive. So this kind of condition you can able to get if XL is equal to XC. If it is XL is greater than, if XL is greater than XC, then my pi value is coming positive. My pi value is coming positive. But what about this angle? It is leading or lagging? It is because here my XL is greater, it means it is a inductive load, inductive domination load, inductive dominating load. So obviously my pi is coming positive, where my current lags voltage. If my XC is greater than XL, then my pi is negative. Now if you want, you can see from this diagram, so that you can come whether it is positive or negative. It's coming like this. You can visualize that things. Okay. So if it is like negative, it means here my capacitor is more. It is my capacitor is dominating. So this is the capacitive dominating load. It is, so if it is a capacitive dominating load, obviously my current leads by voltage. My current leads the voltage. So that is the some point we need to observe here. I will also know here XL is equal to WL, or you can say 2 pi FL. You can know this one. Or XC is nothing but 1 by omega C is equal to 2 pi FC. It means that this XL is directly proportional to the frequency, where here my XC is indirectly proportional to the frequency. So that is the meaning of this XC and XC in terms of this and this. So I know this. What is the impedance equation is, this is nothing but R square plus XL minus XC square. So this is the impedance of the RLC circuit. Suppose if I want to draw, the this impedance versus, if this impedance diagram versus the frequency variation. If you draw the frequency variation, suppose I want to observe, if I increase the frequency, what could be my inductive reactance. So that is the point I want to talk here. If I increase the frequency, obviously my inductive reactance also increasing. It means that as my from the 0 point, as my frequency is increasing, my inductive reactance also increasing in this direction. This is what the my inductive reactance, I can say this is XL. Now come to this second reactance, that capacitive reactance XC. So as my frequency is increases, my capacitive reactance is slowly decreasing. So that is what the relation you are able to extract from this system here. So from the 0, as it is a minimum resistance, if it is minimum frequency, my inductive capacitance is high, and as on my frequency is increasing, slowly it is decaying in this direction. So this is my you can say this is my XC point. So this is the point, I can say intersect point, and this point I can say where this point at this point my XL is equal to XC. Can I say XL is equal to XC? That is the point. But what about my R? R is independent of frequency, isn't it? It does not depend on the frequency. R is always a constant value. So that constant value can be that value you can take. It can be some value. It is a constant value. You can say this is some R value is there. That is the constant. So at this point, if you observe, and I want to again I want to draw the impedance diagram as well here. What could be my impedance diagram here? As my frequency increases, so what is happening to XL and what is happening to XC, and what is this is going to be done here. So if you numerically substitute some values and if you draw the diagram for impedance, so at the initial low value of frequency, my impedance is very high. As on my frequency is increases, my at one point it is going to at a minimum value, and after this point again my impedance value is going to be increases. So this point where it is called a resonance frequency F0. This point is called a resonance frequency F0, because at this moment my XL is equal to XC. Only my Z is completely a resistive value, ZR, completely a resistive value. So that's why minimum value is coming. So after this point again the impedance is going to be adding, slowly it is going to increases. So this is what the meaning. It means, so this is the point. So before this is XL into XC, but in this region, so in this region my XC is greater than XL, and in this region my XL is greater than XC. So this is what the points you can need to understand here. Then what about the current? What about my current? So you know I is equal to V by Z, something like this, you know. So if Z is increases, your I will going to decrease. So this kind of concept you can able to understand here. So as on from this point, if you see, if it is very high impedance, so current is less, and as on my impedance decreases, current increases, and it is maximum point it will reaches, and coming down to this point, so this is called your current. So this is what called you can current is called the current. So this is how you can analyze your RLC series circuit. In the RLC series circuit, as on the frequency changes at a some point of frequency f naught, your XL is become XC. So that point is called a resonance point. At the during the resonance point, the current is going to be become maximum, and the impedance of the circuit is become a minimum. So at the moment my circuit is behaves like a completely resistive circuit. For that, my voltage and current are in phase. So that is what the points we need to you need to understand here. So note. So whenever the XL is equal to XC, then my Z is minimum and I is maximum, where Z is equal to R, and my V and I are in phase. V and I are in phase. So these are the different concept you can able to understand from this RLC series circuit. I hope this you got this RLC series circuit in very clearly, and I will end this session for today.